Hello, my name is Mariana Danilovic. I'm the founder of Infium, and we gather here in Zoom sessions in the virtual Infium salons every other Wednesday to showcase the best of investors, heads of innovation of Fortune 500 companies, and ventures presented by CEOs and founders of those ventures in the Web3, metaverse, generative AI, and other disruptive tech spaces. And today we're going to start with Harry Zhou, who is the founder and CEO of a company called Solid Energies. Welcome, Harry.
Okay, thank you everyone for joining us, and thank you, Marian, for inviting us. So today I'm going to introduce my company, Solid Energies. We're located at Anaheim, Southern California, about 15 minutes from Disneyland. After today's presentation, if anyone is interested in knowing more about our company or invest in us, you're welcome to visit us on site. Who we are, we're established in 2017, focusing solely on solid-state lithium battery development. And we have, over the past 6 years, we have had funding from U.S. DoD, Navy, Army, Air Force, and DOE, and California Energy Commission, total about $7.2 million. With that, we built our IP portfolio focused on 3 areas. One is solid electrolyte with high ionic conductivity and a wide operation temperature range. And 2 is the special manufacturing process for making the solid electrolyte and the solid-state battery. And number 3 is our high-capacity anode and cathode material. We have total 8 patents supplied, and 3 has been approved, and 5 is under review. And currently, from BP business development standpoint, and we have partnerships established with major aviation companies like Boeing and Lockheed Martin, and also we're in discussion with EV OEMs, GM, Stellantis, Rivian, and some others. Looking back at lithium battery industry, currently the major challenge we're facing is first is safety. Everybody knows it's flammable and highly reactive, and also have limited operation temperature range. The second issue is energy density. Everyone has been approaching 260 watt-hour per kilogram energy density, and it's been that for many years. And then the third one is the cost. And the rare metals such as cobalt are very expensive. There also, from system level, it also requires complicated thermal management system, and that adds to the weight and cost. Currently, all the industry experts all agree that solid-state battery is the future. However, there are a lot of R&D and investments in this area too. So, however, this current technology also have a lot of drawbacks, mainly 3 of those. One is the temperature range. So the solid-state battery is usually at low temperature has poor performance. Also, manufacturability. None of the companies has made mass-produced cells yet, including QuantumScape, which has been IPO'd for 2 years. But ceramic-based solid electrolytes is difficult to manufacture in large size and large scale because it's a brittle material, and you have to make a brittle material into a very thin layer. The electrolyte layer thickness is we're talking about tens of microns, which is thinner than hair. So it's very easy to fracture. It's hard to make it to large size and large scale. And the third issue is usability. Okay, all the competitive technology right now requires external temperature pressure, external stack pressure to maintain good contact for good performance. So how we tackle those issues? So our core technology is a solid-state electrolyte and the manufacturing process. So our electrolyte is a polymer ceramic based. It's composite. is a composite material which is flexible. It's solid, but it's flexible. It's almost like rubber. So it's also made of non-flammable material. So it's resistant to the puncture flame. So it's safe and flexible. The second thing is we can achieve high energy density, use less material, and also we can sustain higher voltage. Currently, liquid electrolyte voltage is about 4.4 volts, and we can raise that to 5.5 volts. And then the third advantage we have is the temperature range. We can our cell can operate at minus 40 degrees Celsius up to plus 90 degrees Celsius. We also need to know stack pressure. So in our special manufacturing process, it's because our material is flexible, so it can be made into large cells easily. In the lab, we use manual process. We can make a 50 amp hour, 50 layer pouch cells. And also because it's flexible, it can be adapted to the roll-to-roll process that's currently used in the lithium ion manufacturing process. So we can use existing equipment and existing process. No need to reinvent those. And also, we can simplify the process because our electrolyte not only replaces the liquid electrolyte, also replaces the separators. So we have one process replace two, so we can simplify the process. Some simple benchmark. So if you compare it to a well-known company like QuantumScape, Solid Power, from manufacturing capability point of view, we can manually make 50 layers, 50 large cells, which is industry leading, and also require no stack pressure. And comparatively, like QuantumScape and others, they all need much larger pressure than atmosphere pressure. And then also from charging, discharging point of view, we can do 5C continuous and charge discharge, which means 0 to 80% as full. In a supercharging condition, that can be completed in less than 10 minutes. Our the biggest advantage is the temperature range. We can do minus 40 to plus 90 C, which nobody can do right now. And our energy density right now, we're achieving about 350 watt per kilogram. It's also industry leading. To recap, in summary, our advantage is safety, high energy density, and a wide temperature range, long cycle life. And also we can do fast charging, discharging, and we can easily adapt to a mature manufacturing process for mass production. Some little bit about the cost. Our cost compared to current the NMC battery, which is used in Tesla cars, is we can use the same cathode material, anode material, and the casing material. The only difference is our solid electrolyte that replaces the liquid electrolyte and separator. So our electrolyte is a little bit more expensive than the liquid electrolyte. The worst probably double, but still overall we achieve about 5% total cost advantage. Our Gen 2 product will use high voltage, low cost material like LMNO, which can achieve greater cost savings because it's cobalt free. So it's much cheaper than the current material. And also while we can achieve higher energy density. A little bit about market, battery market, three major markets. First, of course, is EV markets, and second is defense and aerospace, and third is the medical devices and consumer electronics. Total market estimated by 2030 is about over $300 billion. And our target is capture 3 to 5% of that, which equates about $10 billion by 2030. So the roadmap, we're currently at step three, large pouch cell, and we're trying to get to that step 4 with this fundraising. We're doing a Series A. Previously, all our funding is from a government sponsored grant, so we have no dilution for funders equity. So this is the first time we come out to raise money in private market, and so we call it Series A because we already operate for 6 years and we spent $7 million. And yeah, so this funding purpose is to establish a small pilot scale production line, so we can do semi-automatic production and fine tune our process for mass production. The next step for Series B, we're going to do the real pilot production for a 5 megawatt per year production line, and then get ready for Gigafactory build up. So this is our detailed work scope for of the next 12 months with the Series A funding. So just in one sentence is to establish a small pilot scale production line. Last is the team. Dr. Lin is the CEO and founder, and myself, Harry Zhou, I'm the co-founder and product and strategy, and Kevin is marketing and sales. Dr. Tan is our lead scientist. So, and also have two advisors, Professor May and Mark Hastings from finance and investment advisor. So, talk a little bit about Dr. Lin. He has been PhD in material science from UC Irvine in year 2000, and after that he's been focused on nanoparticle and battery material R&D. And myself, Harry, and I was mostly from automotive background. I spent 20 years in Detroit, working for Detroit Big Three and Nissan R&D. Over there, I worked in the LEAF program, and then in 2016, I came to California, worked for Faraday Future. I was deputy vehicle chief engineer for FF91, and 3 years after 3 years in Faraday Future, I came out and to do my own startup. Okay, and yeah, and Dr. Tan is our lead scientist. He's had PhD and postdoctoral work on material R&D. So these are the scientists on battery materials. Anyway, that's all I want to present. Any questions, or we can discuss later. Thank you, everyone.